sklearn, model selection, Halving random search CV. Description: Halving random search CV implements a halving strategy for random search, which can be more efficient than a standard random search, particularly when dealing with large parameter spaces. It starts with a specified number of initial candidates and evaluates them using cross-validation. The best performing half of the candidates are then selected and their parameters are further explored by adding new candidates in a smaller search space, which is half the size of the previous one. This process is repeated until a specified number of iterations is reached. Inputs: estimator. The estimator object to be tuned. This should be an object implementing the scikit-learn estimator interface. Param distributions: a dictionary with parameter names as keys and distributions or lists of parameters to sample from as values. Factor: the factor by which the number of candidates is reduced in each iteration. Default is 2. Resource: the resource to be halved. Either n samples or n features. This determines which dimension of the data is reduced. Max resources: the maximum number of resources to be used in the search. Random state: the seed of the pseudo-random number generator to use when shuffling the data. If int random state is the seed used by the random number generator if random state instance. Random state is the random number generator if none. The random number generator is the random state instance used by NP random. Error score: value to assign to the score if an error occurs in estimator fitting. CV: the cross-validation splitting strategy. Possible inputs for CV are none. To use the default 5-fold cross-validation. Integer: to specify the number of folds in a stratified k-fold. CV splitter: an iterable yielding train. Test splits as arrays of indices. Scoring: a STRC model evaluation documentation or a scorer callable object function with signature score estimator. X, Y. Verbose controls the verbosity: the higher, the more messages. Defaults to 0. Refit an estimator using the best found parameters on the whole dataset. N jobs: number of jobs to run in parallel. Predispatch: the number of jobs to pre-dispatch to the executor. Defaults to 2n jobs. Return train score if true. The results of the cross-validation on the training set are also returned. Search IDs if true. Store the search IDs, which represent the indices of the parameter combinations. Outputs: best estimator that was chosen by the search, i.e. estimator which gave highest score or smallest loss if specified. Best params: parameter setting that gave the best results on the holdout data. Best score: mean cross-validated score of the best estimator. Best index: the index in the list of parameter combinations evaluated of the best parameter. Setting: CV results: a dict with keys as column headers and values as columns. That can be imported into a pandas data frame. Scorer: the scorer instance used on the last call to fit. N splits: number of cross-validation splits. Refit time spent refitting the best estimator on the whole dataset. Search time spent evaluating each parameter combination. Mullet metric: where the multiple metrics were evaluated during the search. Paramgrid: a dict with parameter names as keys and lists of parameter settings to try as values. Where paramgrid is the input parameter grid. Train scores: the cross-validated scores on the training set. Test scores: the cross-validated scores on the test set. Search IDs for all the parameter combinations evaluated. Steps: initialize the search with the specified estimator, parameter distribution, and other parameters. Create an initial set of candidates by randomly sampling from the parameter distribution. The number of initial candidates is determined by the max resources and the chosen resource, either n samples or n features. Evaluate the performance of each candidate using cross-validation. Select the top-performing half of the candidates. Reduce the search space by halving the number of resources, either n samples or n features, and sampling new candidates within the reduced space. Repeat steps 3 to 4 until the specified number of iterations is reached. After the search is completed, refit the best estimator on the entire dataset to ensure that it is trained on the full data. Metrics. Accuracy, the percentage of correct predictions made by the model. Precision, the proportion of positive predictions that were actually positive. Recall, the proportion of positive instances that were correctly identified as positive. F1 score, the harmonic mean of precision and recall. AUC, area under the curve, the area under the receiver operating characteristic ROC curve. MSE, mean squared error, the average squared difference between the predicted and actual values. RMSE, root mean squared error, the square root of the MSE. May, mean absolute error, the average absolute difference between the predicted and actual values. Visualization plots. Learning curve plots the performance of the model as a function of the amount of training data. Validation curve plots the performance of the model as a function of a single hyperparameter. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve plots the precision against the recall for different classification thresholds. Fine-tune parameters. Factor controls the rate at which the number of candidates is reduced in each iteration. A higher factor leads to faster convergence, but may also miss potentially good candidates. Max resources determines the total number of resources, either n samples or n features, to be used in the search. Increasing this value will lead to a more comprehensive search, but also increase the computational cost. Resource specifies whether to reduce the number of samples or the number of features in each iteration. Uncertainty methods. Bootstrapping, resampling with replacement to estimate the uncertainty of the model's predictions. Cross-validation, repeatedly splitting the data into training and validation sets to estimate a model's performance on unseen data. Challenges and fixes. Challenge 1. Halving random search CV can be computationally expensive, especially for large parameter spaces and datasets. Sample use case that resulted in Challenge 1: a search with a large number of parameters in a large dataset could take hours or even days to complete. Fixes to Challenge 1. Reduce the number of parameters to search over. This can be done by carefully selecting the most important parameters and setting others to default values. Reduce the size of the dataset. This can be done by sampling a subset of the data or using a dimensionality reduction technique. Use a more efficient search algorithm, such as a grid search or a Bayesian optimization algorithm. Challenge 2. Halving random search CV may not be able to find the optimal set of parameters if the search space is too large or the data is noisy. Sample use case that resulted in Challenge 2: a search over a large parameter space with a noisy dataset could result in the algorithm converging to a local optimum rather than the global optimum. Fixes to Challenge 2. Increase the number of iterations to allow the algorithm to explore more of the search space. Use a more robust search algorithm, such as a Bayesian optimization algorithm. Reduce the noise in the data by cleaning or transforming the data. Challenge 3. Halving random search CV may not be able to handle categorical parameters effectively. Sample use case that resulted in Challenge 3: a search over a parameter space that includes Categorical variables may lead to poor performance, as the algorithm may not be able to efficiently explore all possible combinations of categorical values. Fixes to challenge 3. Use a parameter distribution that specifically handles categorical variables, such as categorical from SearchCV stats. Manually enumerate all possible combinations of categorical values.